Hello. Today we shall be speaking about a concept called continuity. And this is a crucial concept in calculus because you cannot differentiate a function unless it's continuous. And to check continuity, you have to use limits. And therefore, and this is why that was the steps we did before. We start by limits, to study limits, then continuity, then we shall study later on differentiability. Now, continuity in the past, or in the ancient eras, the mathematicians were not interested really in studying this concept. Why? Because all the phenomena all were continuous. But then, because you can always remark this in nature itself. For example, time does not jump from 10 o'clock and 20 minutes to 10 o'clock and 21 minutes unless it passes by an infinite number of instants of time. And same thing when you, for example, you want to draw a graph. You can say, for example, that my hand would not leave the paper. But it's not the case. Mathematicians, they have to make sure that everything is rigorous. And to give you a nice joke to start with, it's said that one day there were three gentlemen, a mathematician, a physicist, and an engineer, were walking in the countryside, and they saw a black sheep. So the engineer said, "What a nice color are sheeps here." But the physicist objected, saying, "No, this is not a true statement. You have to say at least there is one black sheep because you don't know the rest of them." But then the mathematician intervened and said, "But this is even wrong because you have to say there is a sheep. There is at least one sheep, the black sheep." Having at least one side which is black, because you haven't seen the other side. So although this sounds like a joke, but it is completely correct. Mathematicians, they can't just rely on intuition in order to arrive at results. They have to do it through very rigorous arguments. And there were these two mathematicians, a French one and a Czech priest in the late 18th century, that they came up with the concept of limit. It's them who introduced limit, and it's them who have defined continuity. So in this lecture, we shall speak about continuity. And first of all, we shall start about what's the meaning of definition of continuity. Then we shall list some continuity theorems. Then the meaning of continuity on the interval. Then we shall speak about a concept called the intermediate value theorem and another theorem called the extreme value theorem. Both of the last two theorems, they are useful not only in calculus but also in other specialization as well. Now, about the definition of continuity, what's the meaning of continuity? As we said, you can remark it by intuition. You don't have to find a difficult statement to define it. Its stage is to keep happening without interruption. Something which happens continuously without interruption is called continuous. For example, time is continuous, as I said. And for a function to be continuous, the pencil which draws the curve or the graph of the function performs this duty with an unbroken succession. It goes all the time smoothly, so you say that the graph is continuous. But then, what is strange is that mathematicians, instead of studying continuity, they try to find the type of discontinuity. In other words, if they can exclude these types of discontinuities, then they can say, they can state, they can conclude and decide that their function is continuous. So they started by listing the type of discontinuities, and they have recorded 4 of them. The first one is when the function is undefined at a point A. This is a function here, like for example, you have sine x over x, not necessarily this function. And this function at the point A, you see that although it has a limit at the point A, but it is not defined at the point A, and this is the first type of discontinuities that you always meet. Now, the second type of discontinuity is when the function is defined, like here, it has a value at the point A, yet it approaches another value. In other words, this value is not equal to its limit, because the limit of the function is equal to a value somewhere here. Now this is the second type of discontinuity. Now, the third type of discontinuity is when the curve is cut somewhere. It's cut at A. In other words, there's kind of jump. Here you were going smoothly like this, and then once at A you jump to another value here, and then you go continuously, you continue continuously. This is the third type of discontinuity. And then the fourth type, which is the last type of discontinuity, is when the curve has an asymptote. This is a vertical asymptote, and we've seen this before in our last lecture when we were speaking about asymptote, and we said you may have an oblique asymptote, a vertical asymptote, and an horizontal asymptote. And this type of asymptote here, for example, like you have 1 over x squared or 1 over x. This is not necessarily one of them, but this is a kind of, this is the fourth type of discontinuity. So if mathematicians find that the function has one of these types, it's said continuous. If the function excludes or does not possess one of these four types of discontinuity, then you can conclude that the function is continuous. Now, suppose we give some examples. Now here, this one here, the function here is undefined directly because you divide by x minus 2. So this function is not defined at the point x is equal to 2. Here, the function is not defined, yet it has a limit at the point x equal to 2. And you can cancel out x minus 2 from the numerator and denominator to obtain a value around, I think it's equal to 3 if we decompose the numerator. So this function, this is the first type of discontinuity where it's not defined at the point x equal to 2. Now the second type here, this function here, it is defined at the value x is equal to 2 and is given the value 5. So the value of the function at 2 is equal to 5, yet, yes, here it is, so it was 3, yet its value approaches the value 3. In a deleted neighborhood of the point 2, you find that the limit of the function is 3. So the limit is 3, yet the function is assigned a value 5. They are not equal, so this is the second type of discontinuity. Now we have a third type of discontinuity. This curve is cut, is equal to modulus x over x when x is not equal to 0. It's equal to 1 at x equals 0. So it's assigned a value 1 at the point x equal to 0, but there is a jump here somewhere. It was smoothly equal to minus 1 all the time, and then it jumped to 1 afterwards, so this is the third type of discontinuity. Now, the fourth type of discontinuity is like this one, for example, 1 over x or 1 over x squared, etc. This has a vertical asymptote at x equal 0. Here, so it was going smoothly continuous, and then it stopped. And then again, it went continuous, so it stopped at the point x equal to 0. So the point equal to 0 is a point at which 1 over x is not continuous. Now, these are the four types of discontinuities that we have. So what are the types now? So mathematicians try to call them names. The first two, 1 and 2, they are called removable discontinuity. Why are they removable discontinuity? We'll see later. Because you can remove the discontinuity. In other words, a function is discontinuous, but can you change it? Can you transform it into a continuous function? If you can do so, then it's called a removable discontinuous function. In other words, the discontinuity, you can remove it to be able to transform it into a continuous function. So the first two types can be, when we say, cured or remedied from the discontinuity they have. Now, these are the first. Now, the second one, like the one we saw before, modulus x over x, this is called a jump discontinuity because it was going equal to a value minus 1 and then jumps to another value, another level which is equal to 1. So this is called jump discontinuity. And then the third type is called infinite discontinuity. Like, for example, 1 over x or 1 over x squared. So we have now three types of discontinuities, and we don't have more types. Now, the reason why we call in 1 and 2 removable discontinuity, as I said, because you can cure this discontinuity. You can shape the function in a different way. This was the function. The first one was x squared minus x minus 2 divided by x minus 2, which we said that this function is not defined at x equal to. That's okay. That's the first one. The second one, it had here the value 5 at x equal to. In other words, the limit of the function yet is equal to 3. The value was assigned equal to 5. But then you can remedy both and cure the discontinuity from this. You can cure the function from both functions from this discontinuity it has by what? By assigning a value equal to 3 at the point x equal to 2. So now what you have the limit is equal to 3 and the value is equal to 3 at the point equal to 2, x equal to 2. So now the limit is equal to the value of the function, and therefore this function is continuous. So we call it removable discontinuity. You cure it from the discontinuity. While the other two, you cannot do that. So here, for example, this is the first one we had, and this is the second type. Both, I said, are removable discontinuity, and you can see here, look at here. Here you can add up, you can fill the hole here by a point, And here you can move the hole, the point 5, so that it fills the hole at the point x equal to 2, and now you have a continuous function. So you have removed the discontinuity from these two functions if you want. Now, the point is that we don't say for continuous function, we don't say the function is continuous, but we say try to test the point at which the function is continuous. In other words, we ask the question, not that the function is continuous or not. You may do so, but the correct thing is to ask at this particular point whether the function is continuous or not. In other words, you test the continuity of the function at a particular point. So the test is the following. A function f is continuous at a point A if 3 conditions are satisfied. First of all, the function has a value at the point A, at which you seek to determine whether it's continuous or not. So if f of a exists, then you move forward to the limit of f of x. If it exists, then you move forward the limit f of x is equal to f of a. In other words, you do the 3 steps altogether. Of course, in some books of analysis, for example, of which calculus belongs to, this is the broad subject of calculus, so they just mention the third statement to be just concise. Why? Because if the last statement is true, it means that f of a exists. In other words, 1 exists, and if the limit, if they are equal, mean that the limit also exists, so you can discard the second step here, and if they are equal, this is the third step. So you can actually keep on only the third step and say a function is continuous if the limit of f of x at x, or when x tends to is equal to f of a, at the point at which you seek to test the continuity. But usually we do, in fact, in calculus, do the 3 steps in tandem, in sequence. It's easier. Why? Why we do so? Because first of all, you check whether f of a exists. Because if f is defined at a, you can directly exclude the first case, in which you remember the first case at which f was not defined at a. So if it is defined at a, then you can exclude directly the first type of discontinuity. Next, if the limit exists, if f of x tends to a definite limit L, a real value, and definite L, in other words, the limit exists at this point, then you can easily exclude the third and fourth type of discontinuity. But then you move forward. And if f of a equals to L, which is the third, if you satisfy the third step or the third point in checking the continuity of f, if the limit is equal to the value of the function, then you can exclude the second type of discontinuity. So in other words, if you do the 3 steps in the sequence we showed, then you can exclude the 4 type of discontinuities, and in which case the function becomes continuous. This is an example. Show that f is discontinuous at x equal to 0. Here you have an f which is equal to 1 over x when x is not equal to 0, and it's equal to 0 when x is equal to 0. So this function directly is discontinuous. Why? Because the value of the function is 0, yet the limit does not exist from the right or from the left. The limit of this function is infinity and minus infinity, so they are not equal. So yet the limit of f of x does not exist, yet f of 0 exists, and therefore this type of infinite discontinuity, and the function is discontinuous at x equal to 0. Now, usually all the elementary functions that we are used to, or the one that we exposed before, they are usually continuous on their domain, which is a nice thing. We are lucky. For example, the sine, all the sine, cosine, all the trigonometric functions, the sine hyperbolic, the exponential, the modulus x, the cosine hyperbolic, the tan hyperbolic, the secant hyperbolic, all of them are continuous on the set of real numbers on R. The logarithm of x, we saw before, since the logarithm of x is the inverse of the exponential has a range, the open interval from 0 to infinity, and therefore its inverse function has a domain from 0 to infinity. So ln x is defined only for all values of x greater than 0. Now the tan and sec, we've seen that the tan and sec, because the tan is sec, sine over cosine, so where are the values at which the cosine is 0? You have pi by 2, 3 pi by 2, etc. So in fact, these two functions here are continuous on R, except the points that are equal to n plus 1 pi by 2, pi by 2 minus pi by 2, etc. Otherwise, these two functions are continuous. Again, the cosecant and the cotan, these we would not see them often in economics, but it's worth to list them here and to see the points of discontinuity. The strange thing is that the x power n, no, it takes here a long list. Why? Because we've seen before when we investigated the power function, it's not, as a matter of fact, a simple function. It has all sorts of varieties. When n is integer, when n is irrational, when n is irrational, which is not an algebraic function. So you see here when n, for example, is pi e square root of 2, the domain of the function is the values of x which are positive only. Here, for example, when n is equal to minus m, for example, you have r except 0, etc. So you have here all the list for the power function. Now, for the continuity, you don't always use the test to test the continuity of a certain function at a point. There are some theorems which facilitate your task. How? For example, suppose, for example, you have a function which is continuous and you multiply it by 3. Then 3f of x is continuous. And if you have two continuous functions, f and j, and you add them together, you get a continuous function. You raise it to the power n, you get a continuous function. You multiply them together, you also get a continuous function. And also when you divide one by the other, except when you cancel out to exclude those points at which the denominator is 0. In other words, the roots of the denominator. Otherwise, the function, both the quotient is continuous. And same thing when you have a square root, for example, of a function. When f of x is greater than equal to 0, you have to specify, when n is even, you have to specify this condition. But when n is odd, there is no problem. Like x power third, for example. X power third is continuous everywhere. But when you have x power 1/2, 1 over 2, then it's only you have the continuity is for all values of x greater than equal to 0. So here you have all the theorems which you really need. For example, the power function, which we just were talking about, is continuous, as I said. This is continuous everywhere for n element in L. It appears in all varieties of other functions, like for example, polynomials and rational functions. And we've seen those kind of functions before when we classified functions. For example, the one at the top here, it's a polynomial of degree n, and this is continuous everywhere on R. Because x is n, x to the power n, where n is an element of the set of natural numbers, since it's continuous, the summation from the last theorems is also continuous, so you have Pn of x is also continuous. This one here is a quotient, or is a rational function of x, and it's also, like the precedent one, continuous, except at those points at which the denominator vanishes, and we call them the roots of the denominator of q. Find the points at which f is continuous. If f maps x into x minus 1 divided by x plus 1. This is a rational function, and you can apply directly the result before. It's easy because directly here you see that it's continuous on R, because it's the quotient of two polynomials. This one is continuous on R, and this one is also, and this one is also, and therefore the quotient is continuous on R, except those points at which the denominator vanishes. There are what? X is equal to minus 1 here, the roots, and x is equal to 2 or minus 2. Here it is. F becomes continuous on R, except at x is equal to minus 1, minus 2, and 2, which are the roots of the denominator. Now, what about when you have intervals? When you have intervals, the same is true. When you have an interval, for example, something like this. You have, for example, this is an equation of a circle, and you have x squared plus 9 squared is equal to 9, a circle of the radius 3. But you have, when you solve y in terms of x, you have to exclude one of them. You take one branch to make a function, because we said for x, each x there is one y. So this is a function here, which maps x into the square root of 9 minus x squared. This, you cannot say that it's discontinuous at the point 3. Why? Because it does not adhere to the 4 types of discontinuities. Why? Because the limit exists at this point and the function has a value at this point. Therefore, it looks continuous. So what we say that when you have a function which is continuous on an interval, to check the continuity, what you do of the function, you check the value of the function at the point, and you check the limit of the function at the endpoints of the interval. So here you check at 3 and you check at minus 3. Whereas if you wish to check the ones at the in between, there are interior points, and these points you can just check the continuity based on the preceding theorems. So this function is considered, we are asking the question, is it discontinuous or not? No, we say it is continuous. Why? Because, as I said, none of the 4 types of discontinuities apply to this function. Because it is defined at these points, it has the value 0 at 3 and minus 3. And from the right at minus 3, it approaches 0. And from the left, from the right at minus 3 approaches 0. And from the left as 3 approaches 0 also. So you can say that the function is continuous at these points. So a function, we can say now that the function is, if you have a function defined on an interval, a closed interval AB, it is continuous in that interval if it is continuous in the open interval AB. In other words, when you want to check the continuity on a closed interval, you first check the continuity on an open interval. How you check on the open interval? You choose any point inside the interval, an interior point, and you apply the theorem. You apply the theorem based on what? Based on the theorem that we have just mentioned. Or if you are in doubt about one point, you check the continuity at the point. In other words, you check the limit and you check the value of the point. But if it is defined on a closed interval, in which case what you do is that now most of the graphs that you see and the function that we have dealt with, they are most of them continuous, whether in engineering, economics, in physics, etc. Because they belong to phenomena that are continuous all the time. They are practical life, practical daily life phenomena. So they are continuous. But if they end up at some point, then you check just at this particular point. So what you do, you check the value of the function and you check the limit. So here, for example, for this particular function, it starts from A, it ends at B. So you check the limit, the value of the function at A, and you check the limit of the function when x approaches A. Here, A is on the left-hand side. So you approach A from the right towards A, so you take the limit when A tends to A plus. In other words, you approach from the right-hand side because the function is not defined beneath or before A. Whereas here you check the value of the function, again f of b if it exists, and you check the limit of the function when x approach b from the left-hand side. If both are equal, then you can say that the function in this case is continuous on the closed interval AB. Here it is. F is continuous on the open interval, as I said, and the open interval you may not actually, you may not need, as a matter of fact, to check it. But if you wish to check it, you can. You can say you take the limit under the square sign and then you insert, as we said before. We said when you have the limit of f of x to the power n or to the power 1/2, for example, it's equal to the power half of the limit inside limit f of x. In other words, you introduce the limit inside the bracket when you raise to the power n. So here you can introduce the limit of 9 minus x squared when x approaches a, which is equal to 0. This concerning an interior point. Whereas for these 2 points, if you wish to check the continuity on the closed interval minus 3 to 3, so what remains only is to check the continuity at these 2 particular points. So if you wish to check first at minus 3, what you do is that you take the limit when x tends to minus 3, because here what you do is that you take a deleted neighborhood of the point minus 3, which intersects with the domain of the function. In other words, you take the neighborhood open from minus 3 and open from for a value delta, for example, and then when x approaches minus 3 from the right hand side, the value is equal to 0, but the value of the function at minus 3 is also equal to 0. So now the function, you can say that the function is continuous from the left-hand side at the point minus 3, and is also continuous, similarly, equally continuous at the points 3 from the left-hand side. And therefore, you can conclude that your function is continuous on the closed interval from minus 3 to 3. Find the interval in which f is continuous. Now, this function here, it says you have a square root of another function inside, and you wish to study the continuity of this function. So what you do is that you first investigate the inside function, which is inside 4x minus 7 divided by x plus 3. Now it's easy here. Why? Because first of all you have a numerator and a denominator. So with respect, so you have here the function is 0 at the point 7 over 4. And you have to make sure 2 things. First of all, for the function which is inside, let's call it anything, g of x, which is 4x minus 7 divided by the quotient here by the denominator. Now, what you do is that it's of course, like you said before, it is continuous and r, except at those roots of the denominator. So you have to exclude those roots. You have here minus 3, and then also you have minus 4 and 2. You exclude these points. But again, you have to exclude the regions in which this quotient is negative, because you have a square root here. So in other words, you have to make sure that you have to exclude two things. One, the roots of the denominator, and again, the region at which the g of x is negative, because you have square root. Now, so if even you want to know so this is constitute the domain of your function. But what about the range? It's easy also, because here directly you have a point at which the numerator is 0, which is 4x minus 7. When it's equal to 0, x is equal to 7 over 4. So at the point 7 over 4, you get a 0 value for f. And since the function is always positive, so the range must be starting from 0 till infinity. Here it is. Now here we exclude the roots of the denominator, and at the same time we check for the region for which g of x are positive, and you exclude those that are the region that are negative. Here it is. What you do, like we did before many times, you take each bracket separately, x minus 7 over 4, where is it positive? Here, and negative here, and then x plus 4 in the denominator, here is positive, here is negative, and you do your calculations. In other words, you check for your whole quotient, because the quotient is equal to what? To this x minus 7 over 4 divided by x plus 4 times x plus 3 times x minus 2, which are the brackets constituting the roots of denominator, and you end up with this line here. Here we realize that this is a bold point, whereas here we have holes. Why? Because we cannot divide by neither 2, neither minus 3, neither minus 4, because they are roots of denominator. So we cannot include them in your domain of this particular function. Whereas it's also positive here, here, and here. So you can directly say that the domain of this function are the union of these three regions here, except that these three regions, this one here, this one, and this one here also, which is this one, and this one here, this one, the union of these three constitute the domain of your function, and the range from 0 to infinity. But there is one thing remaining, the point 74. All these points inside these domains are interior points, except, look here, this is a limit 0.7 over 4, which is inside, which is element of this set. In other words, this is what you call a half closed interval. So we have just at the 0.74, we have to check just what the continuity from the left hand side. So what you do is that you take the value of the function at this point, which is 0, and you take the limit when x tends to 7/4. If you find it 0, then the function is continuous from the left hand side at the 0.7 over 4, and thus it is continuous on all these or the union of these intervals. And here is what you have. Of course, you have vertical asymptotes, because here you divide by, I said before, the vertical asymptotes, you obtain them by letting the denominator equal to 0. The points, the roots of the denominator, provided that the numerator is not equal to 0 at these roots. So here you have minus 3, which is a root here, so there is a vertical asymptote x equal to minus 3. There is another one here. Here actually it provides 2, so this one here and this one here, and then it starts from the 0.7 over 4 until infinity. This is a theorem called the intermediate value theorem that we find often many applications of it in numerical analysis and so forth. For example, this one here, it tells you what? It tells you that, and it's important because, as I said, it has applications. If f is continuous, we have to read it in an interval a to b, here it is, and this is your graph of your function. And if r is a number lying between f of a and f of b, this is r, you take any number, here you know, here is a, and here is f of a, and here is b, and here is f of b. You take any number r that is inside, or in other words, it lies between f of a and f of b. Then there is a number c, element in this closed interval at which f of c is equal to r. It looks simple, you can just check by intuition. But actually, it is one of the most rigorous and not that difficult, but it is rather tedious to prove it. Why? Because you cannot, mathematicians, as I said, you cannot rely on intuition. They are foolish people. They have to make sure that everything is okay. But to prove such theorem, they have to rely on the concept of continuity. Because if your functions are like that and you take point in between, you don't meet the graph, But here, because the function is continuous, so always you meet the graph by taking an r in between r and b. And actually, one of the applications, it said what? If you take here, if you cut here at p, then there is one c corresponding to f of c here, f of c, at which f of c is equal to r. In other words, when you take r here, you get a point c at which it's equal to r, and this actually, it has many applications. One of them directly, you can, for example, say, let us suppose that f of a is positive and f of b is negative, or the contrary. So if you take r is equal to 0 in between, it means there is a point at which f of c equal to 0. In other words, there is a root for your graph. In other words, your graph meet the point, the x-axis. And actually, this has an application in many variety of fields. For example, one of the applications, it's called the bisection algorithm, and this is known from the time of the Hindus and the Arabs as well, and Fibonacci, the Italian in the Middle Age have known this theorem. What they do is that, suppose they want to calculate, for example, the root of a certain function. What do they do? Here, a function like this, for example, x cubed minus 3x squared plus 2x plus 7. Of course, there are explicit ways of finding the roots. There are Cardan theorem, there is Ferrari, and ways or expressions, because the students at school take only the expression for calculating roots of x squared plus bx plus c, for example, second order quadratic equation. But when it's of the third 3 or 4, at 5 you stop, because Galois said that you cannot find the root in terms of radicals explicitly. But for 3 and 4, there are methods, Cardan and Ferrari, but people don't use them anymore because there is a computer now and there are numerical methods. So one of the numerical methods, very known one, is the bisection algorithm. There are the false position bisection, the one that we saw in sequence called fixed point. There is Newton-Raphson method. There are a lot of methods in order to obtain the roots of equations. But the most important thing we have to know is that all these depend on the concept of continuity, because if the function is continuous and then you take a value equal to 0 between 2 points at which the function change in sign between negative and positive, it means that a piece is located under the x-axis and another one over the right above the x-axis, and since it's continuous, then it must pass by a point at which it meets the x-axis. In other words, you find the root. So what they do, they used to take any two, for example, points. For example, let's say this one, for example, and this one. These are 2 points. Here, the value of the function is negative, and here it's positive. Therefore, there must be a root, since the function is continuous. In other words, it must pass by a point at which we want to locate this root. So what we do, we apply the bisection algorithm. Again, this is one of the applets programmed by the engineer Bassem at Cairo University. What you do, you apply the bisection. And as I said, this is known from the time of the Hindus and the Arabs, Costa ibn Luca and etc. Because it is based on intuition. So what you do, you apply the bisection. When you apply the bisection, what does that do is that it bisects the interval from P1 to P2, which is the interval that you chose, into half. You end up with the point P3. So it says that the best approximation, a better approximation is P3. This is a better approximation from P1 and P2. But then P3, here the function is positive. And here it is negative. So sure, there must be an interval between P1 and P3. So now you nest. This is the same idea of sequence. You nest, you keep closing the interval and tightening the interval on the root. So since this is negative and this is positive, then we choose this as our new interval. And what we do, we use the bisection again. So in other words, we make it into 2 halves. Here it is, we apply the bisection. On what? On P1 and P3. Here it is. So you divide by 2. So again, this is positive. And this is negative and this is negative. So we don't take P1 and P3, but we take P3 and P2 because they are different in sign. So sure, your root is included between, it is located between P2 and P3. So we can now apply the bisection again on this new interval. So you get again here another P3. So now again, this is positive and this is negative. So now the root is inside. Look, the root at the very beginning was located in an interval which is very wide. So you don't know where to find it. It's like, for example, you lost a key and someone tell you, where were you? For example, this morning. If you tell them I was in a building, then you wouldn't find. But if you tell them I was in this particular room, then it's easier to locate where your key is. Here it is. And then you keep tightening the interval until you can locate your root. Again, there is another theorem which is called, again, which is based on continuity, and it's called the extreme value theorem. So the extreme value theorem is another theorem, as I said, based on continuity, and it tells you, this extreme value theorem, it tells you that if you have a closed interval on which the function is continuous, then again by intuition, but this needs to be proved, of course. The mathematicians, they use proofs. They tell you, sure, on this closed interval, the function must have a maximum value and a minimum value. Again, now a function is continuous on a closed interval. Then, since it's continuous, the theorem tells you, sure, that must be a point, for example, C, at which f of C is maximum, and for another point D, at which f of D is minimum. And you can, this, unfortunately, is a sufficient condition for the existence of maximum or a minimum, but it's not necessary. For example, this function here is defined, for example, on a closed interval, but it's not continuous, and yet it has a maximum. This is a maximum value for the function. So a maximum value of the function may exist, and the function may not be continuous. So in order to summarize what we said here in this lecture on continuity, we said that continuity is you can obtain by mere intuition, but mathematicians, they have to study it through tests at the point at which they seek to determine whether the function is continuous or not. And this test implies this test, you have to apply this test in some steps, and it tells you that a function is continuous if the limit of the function is equal to the value of the function at this particular point. And then they also try to locate the kind of discontinuities they have, and they were able to classify or to find 4 types of discontinuities, and we call them, the first one, the function is not defined at a point, or it's defined at a point and then it's not equal to its limit, or there is a jump discontinuity, or there is an infinite discontinuity. For example, when you have, for example, a function of this type, for example, let's say you have x squared minus 1 when x is less than 1, and it's equal, for example, to 4 minus x when x is greater than or equal to 1. A function like this, for example, you have, for example, you have something like this, here the point 1, and you have x squared, for example, minus 1, like this, for example. So here you have, this is the point 1 at which you check what kind of discontinuity this one has. Because here you have to have a hole here, because the function here is defined at the point 1, it's equal at the point 1 is equal to 3. Now, this function has what you call jump discontinuity. Again, when you have, for example, cosine x over x, now you have cosine x is equal to 1 at x equal to 0. So you may have something like this. This is an infinite discontinuity. So you always have many type of discontinuities. Or for example, you may have, for example, something like this: 4 minus modulus, for example, modulus x minus 1 at x is not equal to 1, and 1 at x is equal to 1. So you have, for example, something like this. This is the removable discontinuity. So in fact, there are, as I said, instead of studying, you are free to do what you like. The best thing is to apply the test of continuity, that the limit is equal to value of the function. But if you can locate directly, you can directly notice a kind of discontinuity, one of the 4 types of discontinuity, then the function is discontinuous. And continuity, as I said, is crucial when we study our next lesson of differentiability, because the function cannot be differentiable except it's continuous. So again, I thank you for your attention. And as we always say, all these lessons are uploaded to the sites of the Unitunno Telematic University, which you can use. And until we see you again, I thank you for your attention. Good luck.